Welcome to this lecture. So in our lecture notes we will today speak about section 3.5 about the real radical. So what is the real radical? So let A be a commutative ring always, and we will first speak about what is a real ring. So a real ring, a commutative ring, A is called real, or sometimes you could also call it real reduced. I will say in a minute why. If the following condition holds, that namely for all n in n, if you have a sum of squares in A, then this must be, which is 0. If you represent 0 as a sum of squares, then this can be only in the trivial way. This can be done only in the trivial way, like you can only write 0 equals 0 squared plus 0 squared plus 0 squared and so on. So in other words, if you have such a sums of squares representation of 0, then every AI must be 0. Or in fact, I can just say A1 is 0, because by symmetry all the others AI are also 0. Right? So you might have seen this already in 2.1.2.12c, or I hope you have seen it, because that was one of the characterizations of a real field. So if K is a field, the following are real, the following are equivalent. K is real. -1 is not the sum of squares in K. And this condition which we have just now taken as a definition for a real ring, for a real commutative ring. Now you might wonder if you could not alternatively take this definition that -1 is not the sum of squares. We will come back to this later. So in the ring case, that is not equivalent actually. Why do sometimes people call this real reduced instead of real? Well, that's because you might know one notion of a reduced ring. A commutative ring A is called reduced if for all A in A, if A squared equals 0, then A is 0. Okay? And this is a bit similar. It's real reduced. Okay. So we have that if A is, well, maybe the 0 ring, a ring with just one element, deserves also some considerations. So if, what about the trivial ring consisting just of one element, 0 equal 1? In this case, of course, this condition is of course trivially satisfied, right? Because every element from A is 0. Okay, so that's would be a real ring, right? But in that ring, it's certainly not true that -1 is not the sum of squares. So already because of a trivial ring where 0 equal 1, this condition is not equivalent to -1 is not the sum of squares. But in fact, that's not the only counterexample. So we will see another counterexample which is not the trivial ring in a minute. But one implication is true: if A is real and is not the 0 ring, then -1 is not the sum of squares. Okay, so on the other hand, we will soon see an example where the reverse implication is not true. But this here is equivalent to where exists a prime cone, right? Because, you know, sums of squares form the smallest pre-order. I didn't want this to be italic here. So I should correct this in the lecture notes. So the sums of squares from a preorder, if -1 is not in there, then it's a proper preorder, and every proper preorder is contained in a prime cone. So if -1 is not the sum of squares, there must be a prime cone. On the other hand, if there is a prime cone, every prime cone is a proper preorder when -1 is not the sum of squares. So let's see what 1, 2, 2a was. That was just that sums of squares are the smallest preorder of A, so they are in particular preorder. And 3 to 3 was that you can extend every proper preorder to a prime cone, in fact even a maximal prime cone. So that was this. Here, this implication cannot be replaced by an equivalence, in contrast to a case where A is a field, as we have seen. So an example of this is that if you look at this ring, you look at the ideal generated by x squared in the ring of polynomials in one variable over the real field. In this ring, -1 is not the sum of squares, because if it were, then you would have an identity of a form -1 is the sum of squares of polynomials, of univariate polynomials, plus some g, where g is in the ideal generated by x squared. Right, so, but the elements in this ideal are just the polynomials that don't have a constant and a linear coefficient. The constant coefficient of such a sum of squares of polynomials must be sum of squares of real numbers, so it's a non-negative real number. And this g does not have a constant coefficient, so I have here that -1 is a non-negative real number by comparing the constant coefficients on both sides. So -1 is not the sum of, so that would also work if I just take here the ideal generated by x, right? Why did I take the 1 by x squared? Because this is not a real ring. Actually, it's not even reduced in the classical sense, because the residue class of x, if I square this, when it is 0 in Rx modulo x squared, but the residue class of x is not 0. Right, because x is not contained in the ideal generated by x squared, whereas x squared is. Okay. Next definition. So an ideal I in A is called real if A mod I is real. That means if, so I can write this a little bit easier, like by saying that for all A1 up to AN in R, if this sum of squares lies in I, then A1 lies in I, right? Because what does that mean for the residue classes of the AIs? That means residue classes, the sum of squares of the residue classes are 0. And then this means that the residue class of A1 is 0. Why do I sometimes people call this a real radical ideal? Because you know the definition of a radical ideal is similar. Definition of a radical ideal would just say for all A in A squared lies in I, implies A in I. So proposition 354, let P be in the classical spectrum of A, so let P be a prime ideal. When the following from a prime ideal of A, when the following are equivalent, P is real in the sense that we have just introduced. Or the quotient field of A mod P is a real field, right? That means it possesses an order. And there exists a P, or it is a real ring, you could also say, where exists in the sense we have just defined. And third condition, where exists a prime cone of A such that fracture P is the support of capital P. So here I refer to 3114b. Let's see what that was. It was just a definition of a support, right? Support of P is P intersected minus P, which is a prime ideal. So the real prime ideals are those which are supports of, or exactly those which are supports of prime cones. So that's a nice connection between prime ideals and prime cones. So from A to B, suppose that fracture P is a real ideal. Now we have to show that this quotient field is real. So I take elements from A mod P, and I have to take fractions of these, but I can always take the same denominator, right? Because I can represent finitely many fractions always with the same denominator, of course. So I take the same denominator S to make it a little bit easier. S should be non-zero. So I take the sum of squares of these fractions in this quotient field. And when I can clear denominators, so I multiply with S squared. When I get this sum of squares is 0, since A mod P is real, it follows that A1 is 0, and therefore A1 over S is 0. So that was very easy. So from B to C, so here I used the characterization of real fields which corresponds to this. So now from B to C I will use another characterization of real fields, namely if this quotient field is real when it possesses an order. And yeah, this is an order on this quotient field. So fracture P together with this order is by definition in the real spectrum of A. By the definition of a real spectrum. And of course, P is the support of this, by definition of a support. Okay, so that was very easy, but we used the fact that the real field possesses an order. From C to A, suppose that P is the support of a prime cone. Now we say we want to show this condition for fracture P. Now let n in n and I1 up to n in I1 up to an in A, such that the sum of the A squares lies in fracture P. When A1 hat squared, etc., plus an hat squared. Okay, sorry. So when I write this as, okay, so when I write A1 squared plus AN squared equals some B in P, and when I have A1's hat squared plus AN hat squared equals B hat, and when I evaluate this in P, but since fracture P lies in the support of P actually equals, I know that B lies in the support of P, and so I know that B hat of P is 0. So I get this, and thus A1 hat of P is 0, because here I'm in a real closed field. Ordered field would be enough, so A1 hat of P is 0, and that means A1 is in the support of P. So that's this proposition. Now, our next definition, the real radical of an ideal, is defined by, what's actually, if you remember, what was the usual radical of an ideal. If I is an ideal in A, then the radical of I, sometimes denoted like this, sometimes also denoted like this. This was the intersection over all prime ideals of A that contain P, right? I could also write it in this way, the intersection over all P in spec A that contain I. So that is usually the definition of a usual radical, and here I define a real radical. So here I intersect just over the real prime ideals containing I. Where R spec A is the set of all real prime ideals of A. And the empty intersection, it could happen that there is no real prime ideal above I. The empty intersection has to be interpreted as A, of course. So since every intersection of real ideals of I of A is obviously again a real ideal of A, right? That's very easy to see by the definition of real ideal. Here this condition, right? If the sum of square lies in an intersection of real ideals, when it lies in each of these real ideals, when A1 lies in each of these real ideals, when A1 lies in the intersection. So, and since every intersection of real ideals of A, even the empty intersection, which would be the whole ring, is obviously again a real ideal of A, for every ideal I, the set or the real radical of I is a real ideal of I. In the classical theory, that every ideal, for every ideal, its classical radical, its usual radical, is a reduced ideal, right? Is a radical ideal, right? And these real ideals are also sometimes called real radical ideals, as I said, right? So that's exactly the real analog. That's exactly the real analog. So theorem 357, for every ideal I of A, the real radical can be characterized as this. So why did I refer to 346 here? 346 was this abstract Nullstellensatz. Actually, we will see that this is closely related. So this is analog to a classical result that the usual radical of I is the set of all A in I, such that there exists a K in N0, such that A to a K lies in I. I mean, whether you write N0 or N, actually in the end makes no difference and will be the same here. But here I take normally I just take usual powers, and here I take even powers only. Here it's important that I take even powers. If you want, you could also take here even powers, but that makes not so much. I mean, there is no reason for it, but would be okay. Here there is a reason why I take even powers only. And what's new here is that I have, that I have this sum of squares again. And now you see already that has to do with the real Nullstellensatz. It's actually just the abstract real Nullstellensatz. It's actually just a reformulation of it by 354. Which says that the real prime ideals are exactly the supports of prime cones. I can actually reformulate this because A is in the real, an element A of my ring A is in the real radical of I, means that for all P, for every real prime ideal of A hat of P is 0, but since these real prime ideals are exactly the supports of prime cones, I can write this as for all P in spare A hat of P equals 0. And now by the abstract real Nullstellensatz, I take it with the I to be the 0 ideal. So when this means A hat is 0 on A hat of P 0 for every prime cone, right? So this is then equivalent to an even power plus a sum of squares being equal to 0. Sorry. Sorry. I forgot here something. I'm really sorry about that. Of course, I need to restrict here to prime ideals, the real prime ideals containing I. And then here also. I have to take those such that I is contained in the support of P, and then this implies a hat of P equals 0. And now look at the abstract real Nullstellensatz. That's exactly equivalent to an even power of A plus a sum of squares lies in I. And that's exactly what's written here. So let I be an ideal in A when by this result the real radical of I is the smallest real ideal of A containing I, of course. Like in the classical case, the radical of an ideal is the smallest radical ideal containing this ideal. Here it's the smallest real ideal or real radical ideal, one could also say. Right? Because it's the intersection of all real ideals. And it's containing I and it's real, Okay, so we could also introduce the real nil radical of A. Maybe you know the classical nil radical of a ring. which would usually be noted like this, or sometimes people denote it like this, which with a capital N. So this would be the intersection over all P in spec A, intersection over all prime ideals, or I could just write it like I do here. Could actually just write intersection over spec A, right? And here I intersect over all real prime ideals instead of all prime ideals. So that's certainly, so the empty intersection is again to be understood as the whole ring A. So that's certainly, you know, that contains the usual nil radical. Real nil radical contains the usual nil radical. And it's also the real radical of a zero ideal. Like the usual nil radical is the radical of a zero ideal. And as a corollary, we have that all A, you know, we had this representation A goes to A head, if you remember, right? We had this real representation of A. If you remember this, I can write it maybe with prime cones. Into this direct product of real closed fields, A goes to A head, right? Which we use now all the time, but this was a ring homomorphism, and we said that it would be nice if it were injective. Usually there is no hope in most cases that it's surjective, but injectivity would be nice, or at least we would like to understand the kernel, and would be nice if the kernel is not too large. Here we can characterize the kernel. So that's the kernel of this real representation. And it turns out it's exactly the real nil radical. In other words, the real nil radical, I mean, that's the real radical of a zero ideal, so I can certainly write it like this, where here I use the zero ideal, so I write just equals 0. So it's the set of all A such that some power of A, I mean, if you want, you can also, doesn't matter if you write here n0 or n. Let me think about that actually. Is that actually true? You know, yes, if this is true with k equals 0, when this is 1, when 1 plus such an s is in I, then I could just multiply it with a squared, and a squared times s is again a sum of squares. Yes, it's okay. You could. Doesn't matter if you take n or n0. So here I took n, but I could also take n0. Yes. It's the set of all A such that an even power of A plus the sum of squares is 0. So, and that's a corollary. Yes, it's a corollary. You know, just because this real radical here, yeah, I mean, this uses again, I guess, that supports the real radical, the real prime ideals are exactly the supports of prime cones. So, you know, the A set of all A in A such that A head is 0 is the set of all A in A such that for all P in spare A head of P is 0, and this is the set of all A in A such that for all fracture P in the real spectrum of A in R spec A, that's the real spectrum would be this, but this is R spec A, the set of real prime ideals, A head of fraktur P is 0. So here I use this, right? Here I use this again. Use the equivalence of A and C. And now this is equivalent to A and P. And so you see that this is equivalent to the intersection of a real spectrum of A. This is equal to the real intersection of a real spectrum of A, which was the real nil radical of A. So that was that's why this is true, and this comes just from this. Okay. So that's it for today. Thank you for listening, and goodbye.